Hi everyone. Today I'm going to show you the solutions to the Class 4 homework problems. If you haven't already, please make sure to go watch the Class 4 video, as many of the important concepts such as probability, expected value, geometric probability, and states were discussed in that class. So after watching that video, now we're going to explore these practice problems. A box contains 5 chips, numbered 1 through 5. Chips are drawn randomly one at a time without replacement. Remember, basically what this means is that you take one and then you put it to the side. You cannot redraw it. So all the numbers have to be distinct, basically, until the sum exceeds 4. So it has to be more than 4. What is the probability 3 draws are required? Well, when will 3 draws? Let's just look at any two possibilities. Let's say like 2 plus 4. 2 plus 4 is equal to 6, which is greater than 4, right? So most of the time, as you can see here, 2 draws is enough to exceed 4. But sometimes 2 draws will be 4 or less, and it will not exceed 4. So basically, the only two cases where the sum of the first 2 draws will be 4 or less is 1 plus 2 equal to 3, or 1 plus 3 equal to 4. So these are the only two cases where the sum of the first 2 values will be 4 or less. And in all the other possibilities, the sum will always be greater than 4. So only if these two combinations of two numbers are picked will require 3 draws. And we will never need 4 draws, because no matter what first 3 numbers we choose, we will always exceed 5, always exceed 4. So basically, 3 draws is definitely enough, and 2 draws is most of the time enough. So the time when 2 draws is not enough, there's 2 possibilities where 2 draws is not enough. So 2 out of, well, how many different possibilities are there for 2 of the chips? 5 choose 2 or 10. So the answer is just 1/5. Now let's take a look at the next problem. Miss Carr asked her students to select 5 of the 10 books to read in the classroom. Harold randomly selects 5 books from the list. And Betty does the same. What's the probability they have 2 books in common? Well, let's first count the number of ways they can get 2 books in common. If they get 2 books in common, then out of the 10 books, we choose 2 of them so that they both have in common. So we do 10 choose 2. So we choose 2 books that they both have, right? Because remember, 5 books Harold chooses 5, and 5 books Betty chooses. And there's 2 books in the middle that's in common. So we choose 2 books that are common in the middle. But now Harold has 3 books. Now this is Harold. This is Betty. Harold has 3 books that were not part of the 2 books in common, and Betty has also 3 books that are not part of the 2 books in common. Now out of the 8 remaining books, we choose 3 of them such that only Harold has them. And then for Betty, out of the remaining 5 books, we choose 3 of them that only Betty has. So this is the number of ways of choosing 8 books such that 2 of them are in common, and 3 of them is for only Harold, and 3 of them is for only Betty, which basically means they each have 5 books and they have 2 in common. Now, how many total ways are there to select 5 books for each of them? That's just going to be 10 choose 5 times 10 choose 5. And now we just have to evaluate this expression. This is just equal to 45 times 56 times 10 over 252 times 252. And now from here, we can just simplify our expression, right? So basically, we can just immediately start canceling some terms out. So we know 252 is equal to 9 times 28. So you can cancel these terms, because we know that 56 is 2 times 28, and 252 is 9 times 28. And then from here, we can cancel that. This is 90, and this is 9, so this will leave 10. And then we're just left with 100 over 252, which will just leave 25 over 63. And that's the answer for this problem. Okay, so now let's take a look at our next third problem. 40 slips are placed into a hat, each bearing a number from 1 to 10. And then each number has 4 slips. So we have 4 1s, 4 2s, 4 3s, all the way till 4 10s. Let P be the probability that all 4 slips bear the same exact number, and Q the probability that there's 2 of one number and 2 of the other number. We want to find Q over P. Notice here that we're dividing probabilities, meaning that since the total number of ways is the same in each of the cases, we're really just dividing the number of ways of each of the possibilities, right? Because the probabilities, the denominators of the probabilities, the total number of ways will cancel out. So really, we just want to find how much more likely is it to get 2 of 2 slips or 4 of 1 slip. And we can do that by just simply counting the number of ways of each of those can happen. So in how many ways can we get exactly one number and 4 of that number? Well, we have 10 slips, so we choose one of those slips. So we have 10 different slips, and we choose one of those slips, right, that all 4 slips will have the number of. So let's say we choose 5, for example. Let's say we choose 5. Then we're going to have 4 5s. Then we're going to pick 4 5s. So there's only one way to pick 4 5s. After we select that, okay, out of the 10 numbers, we select one of them, and that's how we select 5. Now there's only one way, because now we have to have all 4 5s. Now, what about, so this is the value of, P. The probability, the number of ways such that all 4 slips lead to the same number. Now, how many ways are there such that there's 2 of one number and 2 of another number? Well, the number of ways such that there's 2 of one number and 2 of another number. We have 10 slips, we choose 2 of them. And let's say so out of the 10 numbers, we choose 2 of them. Let's say we choose like 3 and 7, for example. Now, but there are 4 3s, and there are 4 7s. So now we need to choose any 2 of the 7s and any 2 of the 3s. So there's 4 choose 2 ways to choose any 2 of the 7s, and 4 choose 2 ways to choose any 2 of the 3s. So our answer is just going to be equal to this quantity, which is just equal to 10 choose 2 is 45, times 6 times 6, divided by 10, which is just going to be equal to this value, quantity, it's just going to be equal to the value. So we know this is going to be 270. And 270 times 6 divided by 10 is just going to be 27. 27 times 6 is 162, the answer. And that is the solution for this problem. Okay, so now let's take a look at our next problem. A positive integer divisor of 12 factorial is chosen. What's the probability the divisor chosen is a perfect square? So, well, the idea here is that we want to find the prime factorization of 12 factorial first. So what is the prime factorization of 12 factorial? The bad way of doing it is finding 12 factorial and then prime factorizing, which will take forever. A better way of doing it is to see that, okay, so how many factors of 2 are there in 12? Well, if you remember from the AMC math counts class, we discussed that we can find the number of times a factor will appear in a number and something factorial by just looking at the number of multiples of 2 less than 12, number of multiples of 4 less than 12, and 8 multiples of 12. So if you remember, basically what you do is you do the floor of 12 divided by 2 plus the floor of 12 divided by 4 plus the floor of 12 divided by 8, which is just equal to 6 plus 3 plus 1 equal to 10. So there are 10 factors of 2. And then we have, it's going to be 12 divided by 3 plus 12 divided by 9 equal to 4 factors. 3 plus 1 equals 4 factors of, let me just write it, 3 and 1. This is going to be 6, this is going to be 3, this is going to be 1. So we have 4 factors of 3 and 10 factors of 2. Now what about for 5? Okay, so for 5, we're going to have 12 divided by 5 equal to 2 factors of 5. And then for 7, it's just going to be 1, 1, 1. Because there's going to be only one factor of 7 and one factor of 11. So the prime factorization of 12 factorial is just 2 to the 10 times 3 to the 4 times 5 squared times 7 times 11. Sorry, it should be 4 here, so this should be 5. So it's going to be 3 to the 5. So now that we have a prime factorization, we want to find the probability a chosen divisor is a perfect square. So we can do that by just testing the different factors. So the factor of 2 can either be 2 to the 0, 2 to the 2, 2 to the 4, 2 to the 6, 2 to the 8, or 2 to the 10. The factor of 3 can just be 3 to the 0, 3 squared, 3 to the 4. 5 can be 5 to the 0, 5 to the 2. And 7 has to be 7 to the 0 and 11 to the 0. Because if you have a 7 or 11, it's not going to be a perfect square. Because all the exponents have to be even in order for it to be a perfect square. So we look at the probability of this happening. There are a total of 11 choices for the factor of 2, anything from 0 to 10. And there's going to be 1, 2, 3, 4, 5, 6 choices that make it a perfect square. So 6 over 11 times, and 3 over, so we have 3 possibilities that result in it being a factor of 3. So 3 over, and then there's going to be 6 total possible possible exponents of the power of 3. And then we also multiply it by, well, we have 3 possible factors of 5, 0, 1, or 2. So then we just do 2 times 2 thirds. And then, of course, times 1/2 times 1/2. Because each of those happens with probability 1/2. Since you can either have a 0 or a 1, and it has to be 0 for it to be a perfect square. And now we can just simplify this expression. A lot of terms will cancel out nicely. And we're just left with 1 over 22, which gives us an answer of 23. Since we're asked to find the m%. That's the solution for this problem. So the key idea here is to look at the prime factorization using this formula to calculate. It's actually known as the Legendre's formula. And basically, we can just look at the different possible factors such that it results in a perfect square. Now let's look at this problem. So we have 7 lily pads, 1 to 7. 1, 2, 3, 4, 5, 6, 7. And we want to go 6 steps forward. We want to go from pad 1 to 7, 6 steps forward. And we want to find the probability that we will reach pad 7. Well, the idea here is that we can just do casework, or we can use states. And I'm going to show you both solutions. The first solution, we can use casework. So we can just we can do casework based on how many 1 steps and how many 2 steps we're going to take. So we can either have 3 2 steps and 0 1 steps. We can have 2 2 steps and 2 1 steps. We can have 1 2 step and 4 1 steps. Or we can just have 0 2 steps and 6 1 steps. So these are all 4 different cases. So if these are the different 4 cases, what's the probability of each of these cases happening? So the probability of this first case happening is just going to be 4 choose 1, because it's 4 choose 1 ways to choose 3 choose 0 ways to choose. It's just going to be 1 way, really, because you just have 3 2 steps in a row. I'll say 1. The same thing as 3 2 0. So just 1. So there's 1 way to just have 3 2 steps in a row. What's the probability of this happening? 2 to the 3 equals 8. So equal to 1 over 8. Now we can also have, well, 4 choose 2. So 4 choose 2. It's going to be, let me just move it down so I can have some more space to write. So it can also be just going to be 4 choose 2. So we have 4 steps, and we choose 2 of them to be 2 steps and 2 of them to be 1 steps, divided by 2 to the 4. So it's going to be 3 over 8. So now, next is that we have 1 2 step and 4 1 steps. So the probability of this happening is just 5 choose 1 over 2 to the 5, which is 5 over 32. And the probability of this last case happening, is going to be 1, because there's just 1 way to have all 6 steps, divided by 2 to the 6. So 1 over 64. And now we just sum all these up. And then we can sum all these up to get 8 over 64 plus 24 over 64 plus 10 over 64 plus 1 over 64, which is going to be equal to 43 over 64, which gives an answer of 107. So then they meet all integers are 3-digit numbers. Also, I think it was a little bit unclear, but the reason it's going to be 2 to the 3 and 2 to the 4 is because we're taking 3 steps, and we have 2 choices for each step, a 1 step or 2 step. 2 to the 3, then it can also be 2 choices for each of the 4 steps, 1 step or 2 steps. So 2 to the 4, so on. So basically, for each step, you have 2 choices. That's why I divided by 2 to the 6, 2 to the 5, 2 to the 4, and 2 to the 3. Okay, so now let's get back to the state solution. So now we're going to solve this exact same problem using states. So basically, we have 7 lily pads. So the idea here is we look at all the different states from 1 to 7. So what's the probability of visiting the first lily pad? The probability of visiting the first lily pad is 1, of course, because the probability of visiting the first lily pad, P of 1, let's call it P of 1, is 1. Because we're already at the first lily pad in the beginning. Now what about P of 2? What's P of 2? What's the probability of visiting the second lily pad? That's going to be 1/2, because we started the first lily pad. There's only a 1/2 chance of actually jumping to the second lily pad. And there's a 1/2 chance of directly skipping to the third lily pad. And now we can recursively define a formula to get the number of ways to get the probability of getting to a certain pad is just going to be, well, like I said in the diagram I wrote here, the probability of getting to a certain state, P6, is just going to be equal to 1/2 times P5 plus 1/2 times P4. Because from P4, if you reach pad 4, there's a 1/2 chance of jumping to P5. And if you reach pad 1/2 chance of jumping to pad 6. And if you reach pad 5, there's a 1/2 chance of jumping to pad 6 as well. So we add those up. So in general, we say that P of K, the probability of visiting pad K, is 1/2 the probability you visited pad K minus 1. Because if you visit this pad, there's a 1/2 chance to jump to PK, plus 1/2 PK minus 2. So then we just iteratively write these possibilities. And then you see P3 is just 1/2 times 1/2 plus 1/2 times 1, 3/4. P4 is just going to be 3/8 plus 4/8 divided by 2, 3/8 plus 1/4, which is going to be 5/8. P5 will be equal to the sum of 3/4 and 5/8, which is 11/8 divided by 2, so 11/16. And P6 will be equal to 11/16 plus 5/8, which is 21/16 divided by 2, or 21/32. And then P7 will just be equal to, well, the P7 is just going to be 1/2 of the sum of P6 and P5, which is going to be 43/64. So then our answer is just going to be 43 plus 64, which is 107. Now let's take a look at the last problem. Deborah flips a fair coin repeatedly, keeping track of how many heads and how many tails she's seen in total, until she gets either 2 heads in a row or 2 tails in a row. What's the probability she gets 2 heads in a row, but she sees the second head before the second tails? The second tail before the second heads. Well, in order to get the second tail, both the tails before the heads, we need to have something like THT in the beginning. Tails, heads, tails. The reason is, in order to get 2 tails before 2 H's, but 2 consecutive H's before 2 consecutive tails, we need to have THT, because we need to have 2 tails, but they cannot be consecutive, so there has to be an H in between them. So no matter what, the beginning sequence has to always be THT in order for our sequence to be satisfied. And for example, the reason that no other beginning 3 letters are satisfied, so if you do something like, if you start off with H, for example, then there's no way that we can actually have it. Because then we're going to need to have, let's say, 2 H's before 2 T's. So this is bad. So there's a 1/8 chance of this actually happening. So we have to have THT in the beginning, no matter what, in order for it to be satisfied. So we're just going to multiply 1/8 at the end to whatever we get. Now, after THT, now what can we have? Or let me explain that better way. So now after THT, now what must we have to finish the sequence? We have to have 2 heads in a row. So you have to have something like HH. But then after THT, we can also have maybe an HT. And then we can also have another HH. Because basically, we want to not have any... Basically, we cannot have 2 tails in a row right now. So we can have any number of HT sequences before we get the HH that's at the end. So in general, we have to have THT followed by in between HTs. And then at the end, we have HH. So basically, it's just going to be all sequences of this. Because after THT, we can just do H and then go back to T. And then we're essentially at the same position again. So we can keep repeating this over and over again until you get another HH at the end. So then the probabilities are just going to be equal to 1/32, 1/2 to the 5, because there's 2 choices for each of the 5 flips, plus 1/128, plus 1/512. And then this is just going to be equal to 1/32 times 1 minus 1/4, which is 1/24. The answer for this problem, by the infinite geometric series formula. Just to summarize the solution, we have THT followed by any combination of HTs and then an HH at the end. Now let me show you the state solution. Deborah flips a fair coin repeatedly, keeping track of how many heads and how many tails she has seen in total, until she gets either 2 heads in a row or 2 tails in a row, at which point she stops flipping. What's the probability she gets 2 heads in a row, but she sees a second tail before she sees a second head? So basically, for this problem to do with states, we need to, again, just like earlier, we have to have THT in the beginning, no matter what. And we're just going to multiply by 1/8 to whatever probability we have in the middle. So we have to have THT in the beginning. And after THT, what can we have? So we have the THT state, right? The THT state. So from the THT state, we can either get heads, and additional heads, head, or we can get tails, or we can just get heads, tails. And these will happen in probabilities 1/2, 1/4, and 1/4. So this is 1/2 probability of going to tails, 1/4 probability of going to HH, and 1/4 probability of going to HT. So now we can just write a states equation. So what's the probability of winning from the THT state? So the probability of winning, let's say the probability of winning from the THT state is P, right? So the probability of winning from the THT state, let's just call it P, right? So then we need to find the value of 1/8 times P, because we need to find the probability that from the THT state, she's going to win, Deborah's going to win. So our answer is just going to be 1/8 P is going to be our answer, because the probability of getting THT in the beginning is 1/8, and then the probability of winning after getting THT is P. So now we just need to find the value P, because we know the answer is just going to be 1/8 P. So how can we find the value P? We can write a states equation. So you can say that P is going to be equal to, well, there's a 1/4 chance to go to HH. So there's a 1/4 chance that Deborah will roll 2 heads in a row and then win. So there's a 1/4 chance we win. 1/4 chance that we win. There's a half chance that if you roll tails, so we do like THT and then a T, Deborah loses, because now there's 2 tails in a row before 2 heads in a row. There's a 1/2 chance that Deborah loses. But then there's also a 1/4 chance that you'll go to HT. And if you go to HT, then it's just going to be THT, HT, ... So if we go to HT, now we're essentially back at the same state again. So we're essentially going all the way back here. The reason is that from HT, we just have like THT, and then we have another HT, and then we have another HT, so on. We're essentially back to the same THT state, because we still have THT, and we still have 2 heads before 2 tails, and now we still need to roll 2 heads in a row again. So there's a 1/4 chance to go to HT state, and we end up all the way back at P. So 1/4 chance times P. And then we can simplify this to get 3/4 P equals to 1/4, or P is 1/3. Or so our answer is just 1/8 times P, the probability of getting THT, which is going to be 1/24. And also, for last week's homework solution video, I forgot to do one of the problems. Class 3 homework problem 3. This was the USAMO problem. It was not actually from the USAMO, it was from the AMC 10. But basically, you have to order the word USAMO in alphabetical position, and you want to find which position the word USAMO will occupy. So the idea here is that U is the very last letter of the alphabet, S is the very last letter of the alphabet, and so we're almost at the very end of our sequence of alphabet. So we can really, the easiest way in this problem is just to find the number of possibilities before this word. So USAMO is almost at the end. So now I'll just see the possibilities after USAMO. So after USAMO, there's just going to be USA. So US is the 2 last letters of the alphabet. So we can have USAMO, we can have USOM, AOM, we can have USM, we can have USM, AO, we can have USM, OA, and we can also have USOAM and USOMA, which is the very last letter of the alphabet. So as you can see here, there's just going to be 1, 2, 3, 4, 5 orderings that are after USAMO. And there's a total of 5 factorial equal to 120 total orderings. So that means USAMO will occupy position 120 minus 5 equals to 115. But here's a more generic way to solve the problem. So that will apply even if it's not at the very end. So let me just make this smaller so I can explain the new solution. So now let's explore the more generic way of solving this problem. So let's look for how many permutations of the 5 letters are going to be before USAMO, and then we add 1 for the permutation USAMO. So how many permutations are before USAMO? It can be A. So if A is in the beginning, you can arrange the other 4 letters in 4 factorial ways. If the beginning letter is O, or let's say M, again, there's going to be 4 factorial ways, or 24 ways to arrange the other 4 letters after M. Same thing for O and S, so 24, 24, 24, 24. So a total of 96 permutations with some letter that starts with the starting letter that's not U. Now, if the starting letter is U, now let's look for the permutations with the second letter is either A, M, or O. So now for the permutations that start with U, how many permutations start with A, M, or O? Well, this is going to be, if it's UA, then there's going to be 3 factorial ways. If it's going to be UM, it's going to also be 3 factorial equals 6 ways. Because you have 3 remaining letters and we have 6 ways to arrange them. And same thing for UO. So these are all possibilities. So we add 18 other permutations with even though it starts with U, the second letter is something different. So overall, now we're at a total of 114. And then after we have the first 2 letters U and S, AMO is the first permutation. Because AMO is in alphabetical order. So AMO is the first permutation with the first permutation when you're listing in alphabetical order with the first 2 letters U and S. So we just add 1 here. So we 1. And then we add, so total we have 96 plus 18 plus 1 is 115, which gives us the exact same answer. And that's the solution for this problem. Thank you for watching this video. If you enjoyed it, be sure to like and subscribe to this channel for more interesting math videos. Also check out the other AMC 10 preparation videos for many other concepts like algebra, number theory, etc.